Hello, good afternoon, all of you. Thank you for being for this afternoon. Today, this seminar is organized by Electrical and Electronic Engineering Sectional Committee of IESL jointly with IEEE Best Sri Lanka section. And we are pleased to invite Dr. Kumar Vinayagamurthy, a professor from Clemson University, USA. And he is currently the Duke Energy Distinguished Professor of Power Engineering and Professor of Electrical and Computer Engineering and Automotive Engineering with Clemson University. And he is also the founder and the Director of Real-Time Power Intelligence Systems Laboratory with Clemson University. And his interests are in the research, development and innovation of advanced computational methods for smart grid operation, including intelligent sensing and monitoring, power system optimization, etc. And Professor Vinayagamurthy has published more than 500 referred journals, technical articles, and his publications are cited close to 12,000 times with the H index of 55. And today he will be sharing with us his expert knowledge on intelligent systems applications in smart grids. And please welcome Professor Vinayagamurthy.
Thank you for that kind introduction. Good afternoon or good evening to all of you. Thank you to the Institution of Engineers Sri Lanka for arranging this talk at a short notice and also the last week of the year. And thank you for your presence for my talk. I'd like to point out a couple of things on this first slide. One is the Real-Time Power and Intelligence Systems Lab website, which is let's see if I can, you can see the website address, rtpis.org. So you can go to that website and you'll see a lot of resources in the area of real-time power and intelligence systems. And also the other thing is, if you're interested in getting in touch with me after my talk, definitely you want to get my email address, which is quite easy, gkumar@ieee.org. Besides that, I like to acknowledge the U.S. National Science Foundation. Basically, that is our funding agency in the United States that funds our research, or most of our research work. So whatever I'm going to share with you as a result of the funding from the National Science Foundation. So with that, I'd like to give you a quick overview of the Clemson University, where myself and also this evening we have Prani at the very back there, who is also a PhD student at Clemson University. Clemson University has about 21,400 students. It is located in the state of South Carolina. We are right at the upstate, close to the state of Georgia, 2 hours from Atlanta, 2 hours from Charlotte on the I-85. And we have about 17,000 undergraduate students enrolled in about over 80 undergraduate degree programs. We have about 4,300 graduate or postgraduate students, as you may call it here, enrolled in about 110 different graduate degree programs. Clemson University employs about 5,000 people, faculty, and faculty refers to academic staff and then administrative staff. Clemson University's annual operating budget is about $1 billion, to give you an idea, and we have an endowment about $623 million. And what you see in this second picture is basically our reflection pool. So that's, when we always tell some of our students that if you lost in thought and cannot solve a problem, you go to the reflection pool, and maybe by that time you sit there for half an hour, 15 minutes, have a snack, and then maybe you figure that whatever idea to solve the problem. So it's a beautiful campus. We are on the lake, even though we are away from the coast, about 3.5 hours, about 400 kilometers from Clemson to the coast. But we have our own lake, and we have a beach on the lake. So if you want to go to the lake beach, it's just about within 2 kilometers or on campus. So it's a beautiful place to be in. So with that, let me get into the outline of my technical talk for this evening. I'll give a brief introduction to the topic of intelligent systems for smart grid. Then I'll get on to the smart grid concept. What is a smart grid? And then I'll briefly explain a few things in intelligent systems that are relevant to smart grid challenges. Then I will briefly explain two applications here. One is predictions, but predictions are connected to dynamic energy management systems. I could talk about a lot of different applications in intelligent systems applied to power systems or smart grid, but we don't have the whole night and to stay here. I'm sure you have a lot of other things planned for the evening. My entire 20-something years of work has gone into intelligent systems applications in power. So there's a lot of papers you could read if you're pretty much in every area that you may be interested in. And then I'll summarize after that. So if you have any questions, feel free to ask at the end of the presentation. Just take note of the slide, and then we can address those whatever questions you may have. Or if not, if you feel shy and you don't want to speak up, feel free to email me or talk outside thereafter. So either way, I'll try to get your question answered. So in the United States, if you look at the high voltage transmission, you will see a network like this, 230 kV and above, or 132 kV and above. If you bring the sub-transmission, then the network will look something like this. Now you can see the complex, this looks very complex. The transmission network itself is complex. When you include the sub-transmission, it looks even more complex. There has been several blackouts in the world today, and of all the blackouts, we will note the following three. The North American blackout of 2003, where 55 million people were outaged, is the third most widespread blackout in history. The one in Brazil in 1999, which affected 97 million people, is the second, and the number one is the one that happened in India not too long ago, where 670 million people were left without electricity. So if you look at this blackout, it has a significant impact economically. It also has impacted lives of people. People have died as a result of blackouts. So the impact is tremendously negative. If you also look at the earthquake, for example, the one in New Zealand, Christchurch, 2011, 6.3 magnitude. Basically, that costed 630 millions of customer minutes. And this is the longest in the history of natural events that happened in Christchurch. Obviously, Christchurch, New Zealand, undergoes a number of earthquakes frequently, but this was quite a massive one. So whether it is a transmission blackout or whether it is a natural disaster such as an earthquake, it has a long-lasting impact economically and otherwise. So power system, which is the electricity infrastructure, is one of the many infrastructures that exist today. The other infrastructures would be water, gas, the computer network, the transportation. But of all these infrastructures, the power grid is the critical infrastructure, for obvious reasons that all other infrastructures depend on electricity to drive them, right? So the electricity infrastructure is the critical infrastructure for us to protect and make it resilient so that every other infrastructure is protected. There's no point protecting the other infrastructures if the electricity infrastructure is not, right? It's the backbone, in other words. Looking at the August 14, 2003 blackout, there basically the task force came to the conclusion that the cause of the blackout was not possible to be, the impact of that cause of the blackout could not be minimized as a result of lack of situational awareness. So there were a number of control centers that were watching the blackout unfold, spread, the cascaded outages spread, and nobody in any of the control centers could say where exactly what was happening, and what they could do to prevent it from further propagating. And that was because there wasn't enough sensing on the grid to monitor what was happening as it was happening. It was basically, there was a time delay before you could notice. So SCADA systems were used, and SCADA systems basically are slow. They basically provide data 2 seconds to 6 seconds. So it was not something that could be used to immediately take actions. And even if it could be, things were happening so fast that the human brain could not comprehend, could not take decisions that could stop that. It is faster than the speed of the processing power of the brain. So with that, immediately what comes to mind is what Einstein said. We are familiar with, we all here use computers, and also we use our human brain. So the human brain makes smart, intelligent decisions. The computer, the microprocessors, are able to process instructions very fast. But the microprocessors are not intelligent. They are only able to process instructions at a faster speed. So what Einstein said is that let's borrow the intelligence of the human and let's put it on the microprocessors, so we borrow the speed. So that way we can have intelligence on fast processing. So we need the combination of the the brain-like intelligence and the semiconductor to develop a fast, intelligent machine. So with that, that basically sets a tone to what I'm going to talk from here onwards. When we talk about construction, I know this is the Institute of Engineers, we always like to have a blueprint, right? Or we like to have a plan. Obviously here, if you have a blueprint of a house if you want to build, here is the blueprint of the Oval Office in the White House, and that is the blueprint of the Trump Tower, the President-elect of the United States, and here's a road construction plan. So there's a plan, there's a blueprint before you do something. So this is the Google Map directions. I'm staying at the Hilton Colombo residence, and I was looking at how far should I come to get the Institute of Engineers, and I just did this about just before I got picked up 10 minutes before to see the traffic pattern, and it gave me 3 options there: 12 minutes, 15 minutes, and 15 minutes. And obviously the driver who picked me up took this route to get me here. Okay, I didn't know why, but the 15 minutes, but maybe 3 minutes doesn't matter. But you can see congestion areas. So Google Map gives us gives us a path ahead, what we're going to see ahead, and we can plan. If you want to retire in the United States, here is a retirement plan. Basically, you start savings first, right? You take this path, savings, then you open an IRA account, you open a 401k account, you buy a house, you invest in stock market, and then by the time you get here, you get a lot of cash, and then you're driving safe into retirement. Okay, so that's a retirement plan. Obviously, when you start here and when you end here is about 35 years, all right, 35, 40 years ahead, you're starting here. So this is a path forward. And obviously, you're familiar with this, right? So, you can read, some of us like to go and see what our future looks like, who should we marry, whether we will get married. Our parents are curious about all that. So again, it's a future thing, all right? So what's common in all this that I've shown? It's the future, right? We are basically interested in the future, right? So obviously, we know that the future, if you are an engineer, you know a dynamic system, the future depends on present and past, the next state. For a dynamical system, the future is not just arbitrary, right? It depends on some memory, some states, some past states, present states, the next state equation, as you know. So with that, when you talk about situational awareness, today's situational awareness is a very important topic in the utilities, at least in the United States, where we are interested in knowing what is happening, what has happened, and even when you look at the flight, a flight scheduled to take off needs a lot of planning. The flight path has to be planned, so there has to be a lot of situational awareness before the flight takes off and when the flight is in operation. A lot of sensors to get that awareness, and that awareness allows offline and online during the flight to make decisions, and whatever decisions you take gives us some performance. That performance is dependent on what kinds of decisions you take, and those decisions were basically led by some kind of awareness. So that awareness could be limited, could be a lot, it doesn't matter, but that's what leads to performance. So we have a lot of data, and data basically has to be interpreted or translated into information, and information to knowledge and understanding that leads to decision making and performance. So this is the kind of thing that happens if the pilots or in the cockpit, they have to fly the plane. Certain operations are critical, like the flight. Here we see Emirates flight flying from Auckland to Dubai, 17 hours and 15 minutes non-stop. The longest flight today that exists. The second longest flight is from Dallas, USA to Sydney, 17 hours. Obviously, this is critical in flight path planning. The two critical aspects is the fuel calculation. That we want to make sure you have the exact amount of fuel to land the aircraft at the destination. And secondly, you want to make sure that it's in compliance with air traffic control so that you minimize mid-air collisions. So you don't want to minimize the path and then you have a collision. Okay, so those two things are very critical in flight path planning. Obviously, once you satisfy those two critical objectives of safety, then you want to minimize the flight cost. And minimization of flight cost is basically trying to minimize the choice of the route, the altitude you fly the plane, what speed you fly the plane, and how much loading you have on the flight. That comes as a result of the fuel as well. You don't want excess fuel on board, because excess fuel on board will basically burn more fuel because of the weight of the plane. So these are all very stringent optimization problems. And furthermore, these are all done before the flight. And on flight, you need to also, the pilots, the captain has to make decisions sometimes that can be different than what was planned before the flight. And that's why we need accurate weather forecast. The accurate weather forecast is critical because your headwind and tailwind speeds are of importance. If you have a tailwind, obviously you are fine, but if you have a headwind, then you are not going to be, right? So you will burn more fuel. So this weather forecast, accurate weather forecasts, are more critical in flight for flight so from one point to the other than any other applications today. So I will give you an example. This is probably the fourth longest flight between Atlanta to Johannesburg, and here is the normal flight path from Atlanta to Johannesburg, South Africa. I was on this flight some time back, and obviously, as you see, this plane and this plane are the same plane. This can fly 17 hours, 15 minutes on full tank, and this one is 16 hours. But now you understand that the flight will not have 100% full because that's how it is planned. So this flight had just enough for it to go from Atlanta to Johannesburg. But what happened was that there were some inaccuracies in the weather forecast, and this plane could not land in Johannesburg, South Africa. And the pilot only came to know that an hour before landing, and that means we were somewhere right here, okay, just flying over the ocean, right? At that point, the pilot decided, I'm going to fly, with enough fuel, I will be able to land in Cape Town and not in Johannesburg. We were like a few minutes short on the fuel. So these are critical operations, and planning is a key. And also the pilot's decision, luckily enough, we had enough to land in Cape Town. So what am I trying to bring out of this examples? Basically, it is the intelligence and the ability to change the action. Okay, so there must be enough situational awareness or situational intelligence to change the course of action. Okay, so you might be wondering, why am I telling you all this? What is it all got to do with smart grid? Be patient and you will get to understand that. So we talked about situational awareness, but what I'd like to share with you this evening is situational intelligence. So situational intelligence is basically looking ahead how situations will unfold over time. It is where you immerse yourself into the future, where you dream. You dream in reality, not just dream for the sake of having a dream. Obviously, we go to sleep, we have nice dreams, we enjoy it. Sometimes we have nightmares, we don't. But here, the dreaming is for taking actions, real-time actions eventually. So the dreaming is going into simulations where you're able to see different pathways, different trajectories, and you see a set of trajectories, and you select the optimal trajectory. That's why you need to immerse yourself into the future. And this is possible today with all the computing capabilities that exist. So what we're trying to do is, in situational intelligence, we are trying to have situational awareness for a future time that we haven't got there yet. Situational awareness is taking data from sensors and processing the data and analyzing it and making some understanding of what has happened. So the data has already been transmitted, whatever actions or whatever event has happened, now you're just analyzing it. So that gives you situational awareness. So it is after something has happened. After the lights have gone out, we figure out, oh, lights have gone out. Okay? But it's already after the fact, it's post. Whereas situational intelligence is knowing that before it happens. So that's why I said dreaming. Right? You have a nice dream. You know, in the Bible you have Solomon or people who dreamt a lot of things to happen, right? And also likewise in many other historical books you find about dreams, okay? And there's interpretations of dreams. So here we want to know, can something happen? And then if it's good, it's fine. If it's not good, we want to take actions to prevent that from happening, right? That's where situational intelligence comes. So we want to derive situational awareness at time t and project it to a time t plus t, okay? Basically, that's what we want to see. So now, keep everything that I've said fresh in your mind as we move into smart grid, okay? So smart grid, the Energy Independence and Security Act of 2007 put out by the US Department of Energy basically said for a grid to be modernized or be called a modern grid, it must have a certain functions that will qualify it as a smart grid. And this includes all the following. One, it should be have the capability or a function of self-healing, fault tolerant. It should be able to integrate dynamically all forms of energy generation and storage. It should be able to dynamically optimize its operations. It should be able to participate capabilities for demand response, have active electricity clients, and overall it should have improved reliability, power quality, security, and efficiency. So when you look at this 7 bullets, self-healing refers to the grid. If there was a outage, part of a section of a grid gets outaged, the grid should have the technology to recover itself. So let's say there's a customer at the end of a radial line, a few customers at the end of a radial line. If there was an outage at the very beginning of that radial line, every other customer past that switch that was open will be blacked out, will not have access to the electricity. But if you had a mesh network, you could figure out which switch to open and which other switches to close, so that no customer or number of customers that see the outage are minimized. So that would be the reconfiguration would mean something like self-healing. Fault tolerance would mean that even though there are disturbances, the grid has enough elasticity to withstand a disturbance. So if there was a short circuit, it could intelligently withstand a disturbance. So some opening and closing, fast detection, things like that. Dynamic integration of all forms of energy generation, what means whether you have variable generation like solar, wind, hydrothermal, all kinds of different forms, electric vehicles, energy storage, you should be able to dynamically integrate them, plug and play. Just like your computer has a number of USB ports, you can connect a number of things and it will immediately recognize what you plug in, and the operating system does not crash because you plugged in a USB device. Dynamic optimization is that obviously when we operate the grid, we have to maintain the frequency and the voltage. While we maintain the frequency and the voltage, which is the security of the grid, we also have to make sure the operation is economical. So there must be some mechanism to optimize how to mix the generations, how to have the power flows on the grid such that it is economical and secure, or secure and economical. Demand response, there are customers that are willing to participate in demand response, and obviously utilities would like to see customers participate in demand response so that they don't have to have peak loads. You could basically trim the peak or get rid of the peaks, flatten the load if possible. So demand response provides that kind of flexibility to do so. Electricity active clients participation, that means that if every customer or some customers had rooftop PV, you would be basically offsetting your consumption. When there's no consumption from the customer, for example, if the customer was gone on a vacation, but the PV is still on the rooftop, will be generating electricity or power. That power should not be curtailed, but rather the utility should be able to absorb that reverse PV power flow. In such cases, the customer, the client, the old customer now becomes a customer and a producer of energy. So that's what makes a customer now an active participant. So there must be capabilities from the utilities, flexibilities from the utilities to now absorb power from the customers rather than sending power to the customers. And reliability must still be maintained, ideally 100%. Power quality, harmonics should be minimized, and obviously security and efficiency of the grid should be maintained. So when you think about these 7 bullets, it is really a challenging system. You know, so when you think about the smart grid, it requires a lot of intelligence, it requires what Einstein was talking about, brain-like intelligence with the fastest processor, right? To achieve fault tolerance, to achieve cell healing, dynamic optimization. So when you want to meet all these functions, basically you see that to study a system like this would require different approaches than we are traditionally used to in the power systems of today for modeling, controlling, and optimization. So in the US, in 2008, phasor measurement units, this is a map of phasor measurement units in the United States in 2008. Phasor measurement units are basically deployed on the transmission network to measure voltage and current phases. And you do that at about 30 hertz in the United States. Obviously, you can do it at 60 hertz and 120, but 30 hertz is good enough. Here, probably you do it at 25 hertz, 50 hertz, and 100 hertz. In 2015-16, we have now about 2,500 PMUs in the United States. They have grown over time due to the stimulus funding that came from the President Obama's regime back in 2009 that allowed utilities to deploy massively number of PMUs. So now we have about 2,500 PMUs, 2,500 PMUs transmitting data at 30 hertz, 30 samples per second. So you can imagine now we have a lot of data. If you remember the slide that I showed you about the 2003 blackout, there we had inadequate situational awareness due to lack of data. The data was only coming from SCADA, 2 seconds to 6 seconds. Now we have at least 120 times faster speed of data. We still have the same problem. We don't have any closed loop applications using PMU data at 30 hertz. Today, the system operators complain that we have a lot of data and we cannot comprehend the data at this speed. Back then in 2003, there wasn't enough data to see what was happening. So we're still in the same bucket of problem here. So if you think about the entire grid, the transmission, the distribution, the microgrids, the customers, every end-to-end is going to be smart. That's what the smart grid is about. The customer is smart. We have smart customers. We have smart microgrids, or we have smart customers, smart nanogrids, smart microgrids, smart distribution, smart transmission, smart generation. Everything end-to-end is smart. Okay, which means everywhere there is data, right? The customer uses data to make decisions. The distribution utility uses data. The transmission. Everybody is in for business, right? Even the customer. The customer wants to save money, wants to buy that electricity at the cheapest cost. In the near future, the customer will be selling electricity. Okay. Today we have Uber, right? The transportation. And in Sri Lanka, do you have Uber? No. All right. So we have Uber. Before we have taxis, right? Now we have Uber. You have an app. You can call a Uber, and anybody can basically. I could basically be a Uber driver and go out and fetch somebody if I am bored. My students don't want me to teach work with them or research. I might just get bored and I might do Uber, right? Just get an app and I'll just go drive people around, right? Soon, every customer that has a rooftop PV will become a small utility, all right? Just like the Uber, you've now become and you can sell your electricity, right? You just buy homes, put PV panels, buy electric cars, store energy, and you'll be selling, right? With all the apps and the computing, it doesn't take much. Soon you'll be rich, right? So, but what is all this going to create? It's going to create big data, right? Everything is about data. The person that's going to make the most return is the one that can process the data fast, right? So we're talking about a large volume of data that is going to be streamed very fast at a high velocity. There's a number of data things that you have to look at. If you're having renewable sources of energy, you have to look at what is the forecast, who is doing the accurate forecast, not just forecast, but who is giving you the most accurate forecast, the energy storage, who has the energy storage to store energy when it's cheap, who has the energy, who has the large state of charge in the energy storage when energy is expensive to sell, right? So it's like going to be fluctuating real-time price market. It's like it's an energy market, right? So and then the price is going to be fluctuating. So based on what sources are available, what amount of energy is available, what's the load demand. So you're going to see that at the distribution level. You're going to see that at the microgrid level. You're also going to see that at the bulk power level as well, at the smart transmission. So you have these 5 V's. The veracity is the imprecision that comes with all this data, and the value is the real time. So the value is when something is in demand, when something is needed, that's when you got to provide it. There's no point for me to give you lunch or dinner at 2 a.m. in the morning. You want dinner somewhere between 7 p.m. and 10 p.m. If I give it to you at 2 a.m., you said, no, I'm sleepy, I don't want dinner. Right? There's no value of the dinner served at 2 a.m. If the dinner is served between 7 p.m. and 10 p.m., it's of value. So that's the other thing here. If the data is not there when you need it, it's of no value. If you're late, it's useless, right? Pointless. The next thing, the 6th V, is basically the visualization. So obviously the system operators in all these different operation centers want to understand the data to be able to take the right action, to take the best decision that leads to not violating any constraints, but at the same time maximizing customer satisfaction and revenue. Okay, because we are all in business, right? We want to make sure we do not just get maximum revenue at the expense of customer satisfaction. We want to make sure we hit an optimal customer satisfaction as well as maximize the revenue. Right? It's a tough optimization problem. So what do? We have to present the data in visualization. You know, a picture is worth 1,000 words. So how do we turn this data into pictures that can immediately spark the action to make the right decision, right, in the brain? So you have to still dealing with human computers, human-computer interaction. The computers have to come up with the visualization. The system operators are the humans that have to connect. So that's the 6th V. So when you talk about smart grid big data, in my opinion, I talk about the 6 V's. Okay, so in all this, what we're talking about is data is mission critical, right? So we want to turn that data into all this into value. That's what we're talking about. So here in this slide, basically again coming to that point of serving dinner at 2 a.m. If we ignore the latency, which means the communication time to take data from point A to point B, you might end up with a graph like this. This is showing an oscillation in a generator. But if you consider just in time, make sure that the data is not late, the data arrives just when it's needed, you get this kind of graph where the oscillation gets damped quicker, right? So this is just an example to show you in power systems, disturbances can be minimized if data arrives just in time. Okay. So what is intelligent systems? Because my title of my talk is Intelligent Systems Applications in Smart Grid. So when we talk about intelligent systems, there are certain goals of intelligent systems. So here are 3 goals that I use to describe intelligent systems. Number 1, full utilization of knowledge of a system and or feedback from a system to provide reliable response. Response here could also mean decisions, control actions, and this is in accordance with some pre-assigned performance criteria. So you have to define some criteria that qualifies as reliable. And obviously here we're talking about full utilization of knowledge, and if you remember one of my previous slide, knowledge is derived from understanding, understanding from information, information from data. I'm assuming you have the knowledge and now you can use that knowledge to provide reliable response. Number two, use of the knowledge to provide response to the system in an intelligent manner as a human expert may function in the light of the same knowledge. So a computer system would do exactly the same thing or better when the same knowledge is given to a human and is given to the computer. Okay? So now a human is compared with a computer system, right? Third, improved ability to provide response to the system over time through the accumulation of experiential knowledge, which means learning from experience. We all learn from experience. When we have a bad experience, we don't repeat that. When we have a good experience, we like to repeat that. It's the same, it's a concept of reinforcement. The reinforcement with a good deed comes a reward. With a bad comes a punishment, right? That's the concept of reinforcement learning. So the human brain learns from experience. So if we can see in a computer system these three features, we can classify that system as an intelligent system. Okay? So intelligent actions is a form of response derived from a system's ability to basically comprehend, reason, and learn about processes, disturbances, and operating conditions. So this is a continuous thing. So the human brain has this capability. If the machine, which in this case the computer, has this capabilities, then you can say that that machine is an intelligent system. Okay? So now you understand the challenges of smart grid, what is the features, the 7 bullets that I mentioned. You understand what I mean by intelligent systems. Can we now marry the two? Can we bring intelligent systems to the power system? Then that makes the smart grid, right? So in order to do that, let me I'll go through the next slides and you see how we do that. Okay, so obviously models, and we talked about situational awareness, situational intelligence, and models are derived from basically this situational intelligence and situational awareness. Okay, so we have in this chart a real-time wealth of knowledge, which is basically what I call as the model. Keep in mind here I said it's a real-time wealth of knowledge. So it is dwelling in the present. Okay, it is a present system connected to reality. Okay, it's a computer's program or computer model connected to reality through senses. Obviously, then there's another module here that makes sense making, that's able to turn that data into that knowledge that I talked about. Uses that knowledge, some historical database, real time, to come up with a set of decisions. So it's a set of decisions, which means there's more than one possible pathway. Like I showed you in the Google map, to get from my hotel to here, there were 3 possible paths. Okay. Ultimately, only one path was taken. That comes to the adaptation. The adaptation is where you look at the physical constraints and you pick one of those in the set. All right. So this whole thing, developing a real-time wealth of knowledge, be connected to reality. Okay. Know what's happening on ground. Making sense of it. Coming up with a set of decisions. Picking the right one. This whole thing is referred to as the CSTM, which stands for Computational Systems Thinking Machine. Okay? If you want to read more about it, I have written that in this paper, and you're welcome to download that from my website as well. So the Computational Systems Thinking Machine has the capability to handle an evolving, uncertain, variable, and complex smart grid. So the smart grid now, from those 7 bullets, is constantly evolving because the load is changing. More customers are coming on the grid. The renewable sources, variable generations are fluctuating, so uncertain. And more people are buying electric vehicles, there's more variability in it, and the complexity of the smart grid is much more than the traditional power systems, because the smart grid is a system of systems. It involves the communication network, the computer network, the financial network, all kinds of other infrastructures are basically buried inside the smart grid. So the computational systems thinking, as I mentioned, needs these three strands, which we have already talked about. Constantly in this, there's three things happening. Computations are running all the time, communications are happening all the time, and there's always controls or decisions or actions taken all the time. What's the important thing to also realize is that in this real-time wealth of knowledge, there's always continuous refinement. That means you're always connected to reality. Okay, you're always checking with the ground physical power system through your sensing network, and through your actuation. Your actuation is going to change the states of the system, and you need your sensing network to provide that feedback. And then also this real-time wealth of knowledge constantly learns, at the same time unlearns. I know some of us are familiar all the time thinking that we have to learn, but we forget that sometimes we also have to actively unlearn. Okay, there are certain things we have to, you might have heard about this, in English we say we have to let go, right? You have to let go of certain things. If you hold on to your past, it can hold you from progressing, right? So the same thing here, this real-time wealth of knowledge has to let go of certain things. So you have to actively unlearn. So this is very important in the systems. So that's basically what happens in the understanding, the knowledge and the understanding. Also, so when you think about the United States, the North American electric power system, it's today the single largest machine ever built by man due to its large connectivity through the country Mexico, through the continental United States to parts of Canada. So how do we, in intelligence systems, one of the problems has been, how do we scale up? Okay, people have said, oh well, you know, all the problems that you have tried with intelligence systems are called toy problems, which means they're small, they're not scalable. So how do we scale up this intelligence systems? Okay, believe it or not, the brain, right, has 10 to the power of 14, 16 neurons. Okay, a massive number of, each neuron is a processor. Okay, and each neuron is connected to about 10,000 neurons as inputs. So if you can think with me, 10,000 inputs to every processor, and they are 10 to the power of 14 processors. That's a massive network. Okay, there's no network as the brain network that exists today. Okay, we carry that in our brain, in our skull. Okay, so that's very scalable. Okay, but now we talk about physical system like the smart grid. How do we scale up? So I talk about the coexistence of CSTMs. Now all of you know what a CSTM stands for. It has 4 modules: the model, the sense making, the decision making, and the adaptation. So in order to implement CSTMs for the smart grid, we have to have this kind of collaborative CSTMs. In a way, when you look at this, you think about it as a distributed CSTMs. Okay, obviously they have to be harmonized, which means they cannot adversely impact the other CSTMs. There has to be coordination, and there has to be communication. All right, so we can implement CSTMs for different areas of the power network. We can also implement CSTMs for every distribution network, right? So when you think about it, you're going to have a hierarchy of CSTMs in harmony, coordinated, and in communications. That's how you achieve the scalability. So how do you realize these CSTMs? Basically, I like to introduce to you cellular computational networks. Cellular computational networks is basically where we bring cells, okay, together in a distributed, connected fashion to achieve a massive intelligent machine. Okay, we can have cells connected like this, and in each cell, what is important is shown here. This is showing a cell. There are 3 units in a cell. The first unit is the computational unit that takes some inputs and gives out an output. Okay, just like the neuron. Okay, it takes an input and gives out an output. Obviously, there is a communication unit. Otherwise, it cannot receive inputs and it cannot give outputs. So the communication unit is there, and then there's also a learning unit which basically provides some feedback to the communication unit, which calculates an output, is a function of the inputs and some coefficients or some parameters. These parameters are changed by the learning unit so that the output matches the target. Okay? Are you all with me? So that's the function, that's the critical unit there. It provides the feedback to correct the output of the algorithm that sits in the communication unit. Okay? So in this architecture, the computational unit can have any algorithm. It doesn't have to be, it can be a time series, it can be a simple addition, multiplication, combination of those, it can be a polynomial, it can be a neural network, it can be any computational algorithm in there that gives you an output based on an input. A dependent variable as the output and independent variables going in. Okay, so that's how the cells will be connected depending on some topology, and I'll explain to you later on how we apply this. So basically, the cellular computational network basically exploits the HTM, which is the hierarchical temporal memory. That's how the brain is structured. The brain is structured in layers, and through the layers is how information flows, and that's how the brain is able to make fast decisions despite a lot of information. Today you have heard about deep learning, but hierarchical temporal memory based learning is much more easier, smarter than deep learning. Deep learning is just a number of mathematical algorithms projected into different space, but whereas the hierarchical temporal memory is more sparse. So when we talk about matrices, here the matrices are very sparse and the processing is much more easier and quicker and still intelligent. In deep learning, you get stuck in deep. Okay, so obviously today there is a hype about deep learning, but in my view, this hierarchical temporal learning has more potential, and one way to do that is through the CCN. The CCN basically can be implemented. Now that you think about the CCN as a combination of cells connected in some fashion, it can be, all the cells can be implemented in a centralized location. It can be decentralized, in other words, it can also be, for example, if you think about a number of substations, each substation could be a cell. Or you could bring all the data into a control center and you can have a centralized implementation. You can also implement it on a parallel platform, a parallel high performance computing, or you can also do it sequentially. Each cell could be processed in parallel. The algorithms that go into each cell could be the same or could be heterogeneous. If substations are identical, the computational unit would be identical. If the functions are identical, then you would have identical. The learning methods in each of those cells could be different, heterogeneous, or could be homogeneous. The way you adapt those parameters could be asynchronous or asynchronous. Asynchronous means the parameters can adapt whenever they need to adapt. Just like all of you are listening to me right now, if you may, I may call each one of you a cell, and you have a brain, and you are learning, you are basically listening to me, and you are absorbing some of the things that I'm saying, and some of you are absorbing at a faster rate, and some of you are absorbing at a slower rate, depending on your experience and your background. So we are using asynchronous updates right now, right? So when we have the CCN implemented, different substations could update based on what the loadings on each substation could be different. Some could have more industrial loads, there's more nonlinearity there, they have more nonlinear dynamics, and the other places could be very simple algorithms that could do. So asynchronous probably is the way to go forward. So what is the best, because the smart grid is a complex system. Obviously we know that the nature that we live in is also a complex system. The ecosystem that we live in is a complex system. We have all kinds of different plants and animals that we co-live with, and it is in equilibrium, right? Our body temperature is maintained constant. We find obviously the temperatures fluctuating in the environment, but they don't fluctuate very volatile. It's not very volatile. It's still, there's some kind of steady state or quasi-steady state, if you may. So we see in nature there is some kind of equilibrium. Nature always gets to equilibrium. How is that possible? Well, there's so many natural algorithms that bring the natural system to equilibrium, which we can learn from. Okay, so here computational intelligence is a field on its own. There's an IEEE Society on Computational Intelligence, which basically promotes some of these paradigms that I've mentioned here: neural networks, evolutionary computing, swarm intelligence, fuzzy systems, immune systems. All this basically are models, computational models that can take raw data from sensors and can process them intelligently in a parallel way, sequential way, providing reliable, just-in-time responses that are highly fault tolerant. So when you think about some of the keywords that I've used in this slide: large, raw, numerical, sensory data, you can immediately associate the smart grid has a lot of raw data. Parallelization, sequential, some of the things can be processed in parallel, and some have to be sequential, and obviously just-in-time, fault tolerance. You can see this seems to be something that runs in parallel with what smart grid demands. So with the framework that I've talked about here, the computational units, probably the computational units can use some of these algorithms. I'm not saying that the CCN has to just use CI algorithms, but can use CI. And obviously neural networks are very good tools for approximating nonlinear functions. Fuzzy logic is very good to make decisions with imprecise knowledge or information. Swarm intelligence are good to arrive at solutions much faster because it's parallelization, swarm. Evolutionary computing is basically saying that the result or the decisions improve from iterations to iterations over time. Immune system means fault tolerance. So all these algorithms have unique properties that are essential or are attractive. And obviously there might be strengths and weaknesses of these algorithms, but combining them, making hybrids of these algorithms, probably allows us to exploit the best features of the different algorithms. For example, if you take a swarm neurofuzzy system, it means that we have neural networks with fuzzy membership functions as weights of the neural network. So instead of having constant parameters, now we use fuzzy membership to have an output of the neural network. So we can handle uncertainty when you have a neurofuzzy system. When we talk about swarm neurofuzzy, we basically referring to several neurofuzzy systems together, collectively, a team, right? So that means convergence can be faster when you have a swarm neurofuzzy. But what ideally you would want is not just a swarm neurofuzzy, but you will want an evolutionary swarm neurofuzzy, neural networks with fuzzy membership functions that can handle uncertainty. You have a population of them so that you can reach the solution faster in parallel. You do a parallel search, and then every neurofuzzy system is evolving, which means it's getting better and better. So what the swarm neurofuzzy was yesterday, we compare that to one of today. Today's one has more intelligence than the one of yesterday. So this is what's going to create an intelligent machine. An intelligent machine will only happen if you have something that can approximate nonlinearities, can accommodate uncertainties, can do that in a parallel manner, and gets better over time. Okay? So those are paradigms of computational intelligence. So how do we achieve capability like the brain? Obviously the brain has the capability to come up with optimal decisions. It means that we can tell ourselves, we can set a target, a performance index, a certain kind of criteria that we tell ourselves, if we attain that, we are happy. We do that all the time. We all say that if I go and see my parent tonight, that's going to make me happy. So we have set that as the goal, going to visit our parents, right? And when we reach there, when we achieve that, when we meet our parents, that happiness just pops up. Because we set the target and we accomplished it. I'm just giving one example, but there are several other examples. Some of you might be writing an exam and you want to get an A or want to get a first class. A 4.0 in the United States is the highest. Here might be 4.2, someplace different. Maybe you want to get that 4.0, right? When you get that 4.0, you reach a state of happiness. That's how you set a goal for yourself. So you set that goal, but at the same time, you can plan the path to that goal, right? You can optimize. If you keep that goal in the forefront all the time, which means you don't forget your goal, you can optimize your path, dynamically optimize. The brain is able to do that. How do we make computer systems do the same? Adaptive critics basically is a technology synthesized from approximate dynamic programming, reinforcement learning, and real-time derivatives. Real-time derivatives is the situational intelligence. Okay. So approximate dynamic programming, some of you may know dynamic programming. Dynamic programming, if you have taken optimal control, you might have heard about Richard Bellman's equation of dynamic programming, the J cost to go function. There we basically calculate the J is a cost to go function that tells you what it's going to be when you go from the initial state to the final state, and what is the total state cost to get to that point, right? If that cost is too high, you can re-optimize, you can change the path to reduce that cost, right? So that's where the real-time derivatives come into play. It provides a feedback. I know I'm here over time, right? How much more time do I have? I can 15 minutes, 20 minutes? Is that okay? All right. Sorry, I went overboard here. So So this real-time derivatives is the intelligence, okay, that is always able to shape. Instead of gradients, instead of scalar feedback, we get gradient feedback, okay, it's more powerful. So I'll go up, speed up here a little bit. So basically the critic network gives you the J function. With the real-time model you can get the derivatives, and you can optimize you can provide some feedback to your optimizer, to your scheduler controller, and that can provide the right control signals. This is a dynamic optimization, okay. Well, now let me get into the applications here. Well, you see this was a very recent picture that I took, we all took. We went to this Relative island in Sri Lanka here, where it's 100% renewables. I understand the official opening is yet to be. Powered by wind and solar. There's energy storage, diesel generator, and the load is about 60 families, mostly fishermen, right? So I was very excited after the conference. We had this tour to this island here in Sri Lanka, 100% renewables. So microgrid basically what's operating there. So now I will get into how we apply some of the intelligent systems that I've talked about, the knowledge, into a microgrid such as the one that I showed you in this island. So if you have all this solar, wind, some load, energy storage, possibly from battery banks as well as electric vehicles, and then also a connection to the grid, what you need is an energy management system that's intelligent. Why do I say that? Well, you have variability here that can be affected, the production can be affected by cloud covers. Some days you have some nice sunny days, some days you have cloudy days. Wind turbines, obviously the wind speed can be quite variable, they have high fluctuation. Sometimes wind blows quite high, sometimes very low, so there's a lot of variability. So that tells you there's a lot of uncertainty. And the load, obviously your customers, and again you're dealing with humans, and the humans are the most uncertain, so they can turn on the load when you don't expect them to turn on the load. And to even add to that, if you buy electric vehicles, charging and charging of those vehicles can change the load quite drastically. And also if you have energy storage, what state of charge should you keep that energy storage? Because what will happen is that when you have excess wind, if you have excessively charged batteries, you have to shut down those wind turbines, you have to curtail them, or you have to have loads called dummy loads, where you just have to dump the generation, which is wasting, right? And if you have low state of charge in the energy storage, and when these are not producing enough, then you cannot pull any energy out of the energy storage because it's low, right? There's no energy there, so your loads have to suffer, or you have to buy from the grid, and then you're not self-sustainable. So in this case, you see, we have to forecast our loads, we have to predict wind and solar energy, we have to forecast reserves, which means energy storage, we have to figure out how to change or dispatch dynamically. Sometimes we have to curtail some loads, and be able to handle all these variabilities. At the same time, we have to be scalable. When we try to scale up the number of customers, the number of wind turbines, the technology must be scalable. So if we have all these capabilities, then we will have a smart microgrid. So now we talk about the cellular computational network. How do we apply that here? So let's say we have several distributed PV systems, okay? And obviously several plants, this could be scattered over an entire city of Colombo, right? And you know that the cloud moves over sections, not all over Colombo will be under cloud cover, right? So we use the cellular computational network to model each PV plant. Okay, each PV plant is a cell, and in this case we are trying to predict the solar irradiance, the cloud cover, if you may. And then if they were like Colombo 1, Colombo 2, Colombo 3, Colombo 4, so we could have a number of cells. Okay, and based on the location, spatial location, we can connect them. So we could know before a cloud cover hits a PV plant, a cloud cover is coming, and we know which PV plant is going to drop, right? So we have a spatial intelligence through this CCN, okay, and that forms the cellular computational, we say, cyber prediction system. So we did this. One of my PhD students, Hiroshini Jawadne, who was a graduate of the University of Peradeniya, she's working on this. So we applied this to some data from Hawaii Island. We took a number of locations, did the spatial modeling, but at the same time we are thinking, like for example here, we could connect, if you want to look at two cells, we could connect them in any configuration like that. If you wanted to study 3 cells, we could connect them, there could be 3 cells. We are trying to predict the solar irradiance at this location, but we could form a number of cell configurations spatially. So again, we could do 4 cells and we could do a number of different combinations. Okay, so there's a number of CCN configurations that you could figure out. Obviously, one or more of these combinations is going to give you better results, the others will not. Maybe 2 cells may not have enough intelligence. This may not have enough intelligence to give you as much as this configuration. This might be too much of an overkill. So we got to figure out some way to figure out what is the best way to get the accurate solar predictions. So she has done this study, and it looks like from our study, the 3-cell configuration gives us a good prediction in terms of mean absolute percentage errors, 11.8%. This is over 24 hours. So this is one application of CCN. The other application is where one of my other PhD students, again this is from University of Moratuwa, Chirag, who's working on. He has applied this to forecasting wind speeds. Okay, again the same concept of spatial locations. We are trying to predict the wind speed at the center location. He's looking at 4 other neighbors, and again we put in a cellular architecture. Each one is a cell. He has studied different computational units in each of these cells, and the challenges in wind speed prediction is the ramp ups, ramp downs, the high wind speeds, the low wind speeds. These are the challenging regions when we predict the wind speed. So again, he looked at 15 minutes predictions, 30 minutes, 1 hour. Certain computational units like this cellular multilayer perceptron gives you 4.3% on the 15 minutes, 5.862 on the 30 minutes. But the recurrent architecture gives you a better results on the 1 hour, because 1 hour requires more memory, shorter times less memory, which makes sense. So these are spatial temporal predictions using the CCN architecture. We are also doing similar things on the frequency prediction of the power system, where we take the nodes, buses, every bus is a cell, and we can predict the frequency. We're doing that also on the generators to control, to do better stability and control, getting the speed predictions on the generators and trying to do that. So a number of different applications using CCNs. So coming back to the microgrid, if we have the predictions of the PV, the wind, then we can know what are the energy availability from these renewable sources ahead of time, whether 15 minutes, 1 minute, whatever time duration, and then we can better manage the microgrid. Obviously, you want a dynamic energy management system for all the reasons I have mentioned to you. You want to have situational awareness and situational intelligence from all these microgrid states. And then basically a microgrid operator is going to set some objectives. Based on that objective, this DEMS is going to implement some decisions. And based on these decisions and again feedback, the microgrid operator is going to get some feedback on the performance and try to dynamically adjust if the performance is not satisfactory. Okay, so so microgrid operator can define any objectives. This is just showing you some load profiles, some energy source profiles. You can see the total combination of wind and solar, and you can see the total combination of critical and non-critical load. So here we have 2 kinds of load: critical load like the hospital load, must be powered 24/7, and we have the non-critical load that needs to be powered, that can be powered when there is excess power, such as the cinema, so today, I'm not expecting you to read this decision tree, but we have a set of rules that we follow and say if there's excess renewables, power the critical loads, and if there's extra, power the non-critical loads, or check the state of charge of the battery. The battery is charged to a certain threshold, now power the non-critical load. So we follow rules, if-then rules, right? That's what a decision tree is. The decision tree is only as good as the person that comes up with the decision tree. Okay, the decision tree is a rigid, fixed system. Okay, there is no adaptability in the decision tree. Okay, there is no intelligence embedded in the decision tree. So what we would like to have is an energy management system, which we call the intelligent energy management system, that will ensure the microgrid is reliable. That means there's a high 100% or availability of energy or power to the supply the loads, self-sustainable, like the island here in Sri Lanka. The generation in-house is enough to meet the load requirements. Environmental friendly, that means it's clean, right, green. Smart grid functionality means it has capability to change power flows, bidirectional power flows. When there's excess energy from a home, it should be able to send it back to the grid. Customer satisfaction, we want to maximize that customers are satisfied, which means reliability and availability is very important. So if we can have a system where we just say this is what we want. Now we take this into mathematical formulas. This is just putting in words what you want. Now you got to interpret this into formulas, into equations, right? So the first objective here is reliability, right? Supply the power requirements to the critical loads at all times. This is 100% reliability. In order to do that, if we have solar, which is out in the night, you get 0. That means you have to depend on the energy storage. So the battery must, SOC, state of charge, must be at certain threshold. So you have to maintain the battery so that you can carry the load, critical load, throughout the night. That means reliability 100%. You want the sustainability, clean energy, maximize the utilization of renewable sources. Then the battery life is also an important thing, because the battery is expensive. If you charge and discharge, the frequency of depth and the number of cycles is exhausted quickly, then the battery has to be changed, which will become expensive. So you don't want to charge and discharge frequently. You want to maintain some kind of cost objective behind the scenes there. So maximizing lifetime is important. And again, the last objective here is to maximize controllable load, which is the load like the cinema load, so that you get better customer satisfaction. So all this can be formulated using the adaptive critics, which I'll show you shortly. The DEMS is the decision tree. The process to start this is that first you can start with a decision tree type of control. You can just clone that, right? You can use a neural network to supervised learning. You can just clone that, and now this can be subjected to learning. The decision tree cannot be subjected to learning. Obviously, if you talk to some people, they say that, well, you can also change the rules, but it's not that flexible. It's still limited. But if you make this a neural network, it has a capability to adjust the parameters or some kind of function that can change its coefficients. Now going to the adaptive critics, obviously adaptive critics is something that I cannot explain in a few minutes, but there's a lot of literature on my website you can look at, on the RTPIS website. But again, it's about the two networks, the critic network providing feedback, learning the cost to go function, and the action network. And here we have a utility function that takes all these objectives that I've mentioned into some sub-utilities. And again, each of this is a mathematical function that tries to use the concept of reinforcement learning. And the idea is that we want to minimize U to be 0. And U to be 0 here means J is minimal. So we are trying to minimize J. So the dispatcher or the action network or the DEMS is going to send out dispatch signals so the dispatch signals are this dispatch signals to the critical load, to the non-critical load, to the battery, the amount that you're going to pull out of the diesel generator, amount you're going to send to the grid, all that are dispatch signals that comes out of the action network. Those signals will be dynamically changed by the value of J. Okay, so this is continuously, it's a kind of a brain that continuously learns, continuously optimizes dynamically. Okay, so besides this is just one unit of that, but because we want to achieve convergence as fast as possible, we create a population of this items, and we use the concept of evolutionary computing to create a number of these populations, and we produce from a parent offspring. So we are doing dispatch every minute. Within 1 minute we are able to have a number of items co-evolve, and we find the best one among that population, and that's the one that dispatches the signals to the microgrid. So this way convergence becomes possible faster than 1 minute, yeah, and it can be parallelized. So here we show only 3 units, but obviously you can have 1, 2, 3 that produce 3 offspring, then you have 6 and you select one out of them, but this can be done to n depending on how many processors you have. So I'm almost towards the end of my talk. Here are some results to show you that the priority controller is the DDEMS and the other one is the intelligent DEMS. Both of them are able to meet the critical load, which means they are both able to maintain 100% reliability. But when you look at the controllable load, which basically accounts for customer satisfaction, you find that the blue line, which is the IDEMS, does gradual switching in and out of customers, whereas the decision tree does abrupt switching in and out. So customer satisfaction here will be less. On the other hand, on the battery, you find that sometimes the decision tree does deep discharges on the battery, which hurts the battery. Okay, whereas the IDEMS does not do that. IDEMS has tried to minimize the depth of discharge to be less. We also formulated some other measures to measure how good our IDEMS is, and one of the first performance index we came up here on the top is basically looking at how much of the renewable energy is utilized to meet the load demand. Okay, and then the second thing is how much of the controllable load was met. Okay, so first thing is looking at sustainability, self-sustainability. Are we using the renewable energy from wind and solar to meet the load? How much of it contributes to the load? And secondly, how much of controllable load are we meeting? The higher the controllable load we meet, it is an indication that the performance is good. We're getting better customer satisfaction. And the second one, we also said it needs to meet whatever we set in the first performance index, but in addition, we are also taking into account the lifetime of the battery. Here we are basically discounting the lifetime of the battery. Here we are accounting also the lifetime of the battery. Okay, so this is a harder constrained performance index measure. So in this graph on the left, you can see this is the DDEMS. Okay, this is showing you the state of charge of the battery. The battery is anywhere between 25%, 35% to 70%. You have a flat line and then it gets better. Here we show you that the IDEMS without considering the battery's lifetime, and here the battery's lifetime. So you can see that the IDEMS gives you a high performance index, which means that it is using more of renewable energy to meet the load. At the same time, it's also increasing, it is meeting higher non-controllable, non-critical loads. On this chart, it's a normalized performance index, which means we are taking this divided by this, okay, normalized PI. So here on this axis is the state of charge of the battery, anywhere between 30% to 100% state of charge of the battery. Here is the battery size. We have a small battery here, 2000 kilowatt minutes, and here we have 10,000 kilowatt minutes. So you can see when we divided this over this, here we already starting with about 1.08 at the base here. That means the lowest is even giving you 8% better than the IDEMS is giving you 8% better than the DDEMS. But the peak here, if you optimize the state of charge and the battery size, you can get 30%. So we are getting 30%, anywhere between 7 to 30% or 8 to 30% with IDEMS compared to the decision tree. Using the adaptive critics and all the neural networks for predictions, we are able to get for the same microgrid, same investment on ground, no higher PV or solar or energy storage, you're getting up to 30% more, just because you have a smart controller that is able to see the forecast, is able to optimize dynamically, and is able to get you that anywhere between 7 to 30%. So if any one of you here is interested in a startup company on this, feel free to talk to me, and we can start up a microgrid where we can give customers 7 to 30% more for the same investment that the others are giving, right? So this is just because of brain-like intelligence that is constantly monitoring and taking actions. So in summary, intelligent systems are critical to fully automating complex systems. Obviously, I've talked about intelligent systems. I've given you examples in smart grid, but it's applicable to any complex systems to provide understanding and predict multiple states over different time scales, to generate the right control response signals under difficult conditions, maintain a high degree of grid integrity and reliability. The operational efficiencies of microgrids and smart grids can be improved by foresight. I'm referring to situational intelligence and optimal control. Okay, it's not about getting the best control, it's getting about the optimal control. Optimal control is the key. If you do good now, doesn't mean you're going to do good in the next time step. You could go up and down, but we want to have an optimal trajectory. That's what we're aiming at here. The straightforward way to ensure sustainability is to use intelligently, freely available sources of energy that are clean and emissions free. I think you will realize here I use the word intelligently. It's not that if we have wind and solar, we are going to be able to harvest the maximum return. It's about putting the intelligence on the processes. Like Einstein said, can we put the human brain-like intelligence on processes? If we can do that, with the investment, we can harvest more. 7 to 30%, as I've shown you in the case study that we did. Obviously, it will be different for other systems. With that, I'd like to thank you, and I apologize for taking going beyond my time. Thank you. So, I'll be glad to take any questions you may have, if you still remember what I said in the last 75-8 minutes. Do you need to come to the microphone maybe to use so that recording?
How about the economical aspects? Because if you look at the village you have shown, it's a very, very poor village. If you are going to develop a mine, already develop mine, is it possible to apply this kind of economic over there? Because very, very poor people and we cannot, they cannot afford. Then how we can balance that with the economical sustainability? Because, economically this is sustainable, but economically how we can balance this?
Yeah, but I think for that particular village, the microgrid is already in place. So now it's to change the way the dispatch management is done, right? Operational management is what we're talking about, operational technology. So that's just, changing the controller there, just doing some forecast of the resources, wind and solar, and possibly providing, if you have to do some curtailing of the load, like obviously one has to study the loads this families have, and I'm sure they probably don't have any sophisticated loads, probably just light and maybe refrigerators. So I mean, refrigerators, the temperature settings could be changed. So I think there it's more about awareness and managing the energy storage. I think managing the energy bank there will be critical, not to run it down, because I think at some point if we don't have a proper dispatch mechanism, the energy storage lifetime could be reduced. One has to study the lifetime of that and how it's currently done. So that might be sustainability. The longer you can prolong the life of the battery energy bank, it will be sustainable. And I'm not sure how much they pay. I've not got into the details of all that, but economics is an important thing when you look at microgrids such as this. Definitely capital investment is high, okay, but operational cost is low in renewable energy based systems, and I expect that such projects will be sponsored by the government of the countries, at least the capital cost, or some investor would put that on and then recover this, not overnight, but today the solar systems, the recovery time is about 7 years, but again the lifetime of this are now projected to be 40 years, so it's about 20%. So there's still enough, it's still attractive for an investor to look into this kind of systems. And I think depending on the communities, obviously I don't think the price of electricity, in my opinion, I think the price of electricity would not be the same from community A to community B. And I think this is where the government, respective governments will come and say, well, if it's community A, it's a fisherman community, we don't expect that to be the same price they pay as we would pay here in the city of Colombo. So I think this is where the policymakers and the government comes in to have a differentiated pricing to make it economically viable. We don't expect the same return in every community. I think if we go with that kind of philosophy and acceptance, these projects will take off. Yes. Yeah, maybe you just hold on till the microphone comes to you, and then.
Professor, are we depending on an internet-based microgrid? Because this microgrid, a smart grid, is based completely on the internet. So, are we putting a vulnerability at risk to our kind of a system? So,
yeah, it's a very good question. Obviously, as I said, it's all about the 3 C's: communications, computations, and control. The communications, we are talking about end-to-end smartness, and we talk about smart customer, smart home, smart distribution, and we talk about the smart home and the smart customer. We are talking about Internet of Things, smart distribution, all Internet of Things. So yeah, it is it's an energy internet. So yeah, we are talking about high vulnerability. With flexibility, with intelligence, with maximum comfort, returns, whatever we get that at the expense of putting more vulnerability, right? So the computer, the communication network security, which is referred to as cyber security, we are prone to that. So that's one of the reasons why closed loop applications of phasor measurement units, a number of advanced manufacture and metering infrastructure are not used in two ways, because utilities don't want to be exposed to attacks. So we need a lot of research work, implementations to protect attacks. So yeah, so you see the good things, and then you see how vulnerable you are, if you want to go after this. So yeah, so that's why massive connectivity of Internet of Things is not existing today. On a small scale it is, because if you lose a small part, it doesn't hurt the entire system, because you can do a cyber attack if it's all smart, networked, and then and still have a blackout. Yeah, so we are not yet there. Yes. So some work is going on in our lab on cyber countermeasures, when we're looking at PMU data. And again, some of those cyber countermeasures we are developing are based on intelligence systems. The intelligence systems have promise for cyber attack countermeasures. Any other questions, comments?
I have another question.
Sure. Maybe
So-
microphone again. Yeah. Oh, you have the microphone. Okay, good.
So, Professor, are there any ways of putting, like, let's say, a smart grid consists of some kind of an AI? So, is there a way of putting an AI, and then AI can be controlled mechanical devices, such as if you can optimize the use of solar, like if the solar panel can be moved side to side with the use of cloud coverage? Is there can we do it actually?
Yeah. So I mean, obviously there are tracking systems already that exist today for solar arrays. That they can track the sun to produce maximum power. But again, it's very expensive. So you have to think about the economical aspect. Do you want the tracking systems? That's the investment cost will be higher. So it's a trade-off versus how much you invest capital and how much power you get. So you have to do that study to see whether it's worth putting the tracking systems or not. But that technology exists today. Okay. It looks like everybody's happy with the talk. There's no questions. Yes, there's one there. Okay.
I think you may have observed what we are doing in Sri Lanka where we are. Based on your observations, what are your recommendations? Where should we go? Where should we start? How far have we gone?
I don't think I'm in a position to comment on that, because I don't know the system much yet. I know very little about the system. I think it'll be unfair if I just comment without knowing the system. So I've noticed power in and out a few times, but yeah, I think what I've heard so far is that there is 100 megawatt solar wind farm coming up in Mana. There is 200 megawatts of blocks of 100 megawatts of solar that's going to be possible to buy, to sell. It's going to be deployed. So those projects are great projects, going towards renewables. And I was also very pleased to see the Ministry of Power and Renewable Energy, so the fact that you have it named as Power and Renewable Energy, that is a good thing. it means that you are embracing renewable energy. And I think the island, Sri Lanka, has great potential for renewable energy. Wind, especially in the west of Sri Lanka, Mannar is I think the greatest potential for wind. There's a great potential for solar across the country. So renewables have high potentials in Sri Lanka. And I think the load in Sri Lanka is not that sophisticated, it's not much. I believe if carefully designed, Sri Lanka can go 100% renewables. With the hydro, you have a lot of hydro, so that's renewables. So you can actually substitute the thermal with wind and solar. And all you need is some intelligent systems for dispatch, for monitoring, more intelligence into the grid for monitoring. And I think that's probably underway. Sri Lanka, I think, can go 100% renewables. Okay. So. Say that again. Sea waves. Yeah, definitely tidal energy. Sea waves, yeah, I think there's potential for that, but I think that is still not matured enough, maybe. I'm not familiar with the technology that much to comment. But yeah, definitely as an island that exists as well. So, the energy is basically the backbone of economy. So I think if we can work on Sri Lanka and can work on the energy, and if there's ample energy, then the economy will grow. Yes.
You want increasing high level of soul, but that we can go for large scale solar or the rooftop type small distributed type.
Yeah. So I think your question, if I understand, is whether the solar should be at large power levels or should be more small power, distributed power, many small distributed PV systems. Well, I think that depends on the network, the power system, the network power topology, and the power system transmission and distribution network. I don't know much about Sri Lanka's transmission and distribution network in terms of day-to-day operations, but you'll be able to study that and see whether the transmission capability is there, because with large solar plants, you're looking at transmission levels, or sub-transmission levels, and for distributed PV, again, you're looking at whether you have just radial networks or you have hybrid mesh and radial networks at the distribution level. So one has to study carefully the existing network, both at distribution and transmission, to see what capacities are there and where the locations for bulk PV integration, as well as where the peak loads, where you have to study if you're going to the distribution, you have to look at the voltage profiles of the distribution network to look at distributed PV and come up with the right reinforcements for voltage. So I think one has to do a detailed study of the network to see how much. I think Sri Lanka will probably have capabilities at both levels of the transmission as well as distribution, but the question is how much, and where so a detailed study has to be done. I think maybe somebody is already doing that. Yeah. And I would say both is good, to have both bulk utility scale as well as small distributed PV systems, because resiliency will come from both approaches. Yeah. Okay. Can you stay? Yeah.
First of all, I would like to thank for giving this kind of knowledge for us. It's a fascinating time. Yeah, when I stood this product. Certainly, we have worked for a technique in Sri Lanka.
Say that again.
As country, we have gone for a technique. It's one part.
Okay, net metering. Okay.
Level of that.
Yeah.
People are, especially in the development area, actually participating for development process of the concept is right now trying to go to more to become better because as you said, the investment is high and long. Other than that, for the smart, you have said smart homes and smart networks and everything. So, what kind of benefits other than anything beyond that? How can optimize the customer based on smart meters at the moment in your area?
Yeah. So even in the United States, even though we have a lot of smart meters deployed, we are not actually using, there's no, to my knowledge, there isn't that very little usage of the smart meter features, which is where really the benefit of the smart meter is, where the customer can actually monitor the usage and optimize the usage of different appliances at different times, have real-time pricing. There's nothing like real-time pricing in South Carolina where I live. But assuming if those capabilities were there, if there was real-time pricing, the time of use pricing was there from the utility, then the customer can monitor their usage and is able to schedule their loads. That means we're talking about a home energy management system, HEMS, right? Then obviously the customer can shift the loads to times when their prices are cheaper. Just little shifting of 1 hour, 2 hours, or even like a washing machine, delay the washing machine till when the 2 a.m. or 3 a.m. and all those kinds of things can be done. So those are the capabilities that we would see in a smart home. A smart home would have real-time pricing information, and if a smart home would have maybe a PV, would able to forecast the generation from there. A smart home might have electric vehicle where energy storage is there, and do this kind of optimization. Again, home energy management system can use this adaptive predicts technology, and that's when every home will get smart and minimize the electricity bill. At the same time, when every home does that, every smart home minimizes the load, shifts the load, ultimately the utility will see the change in the load profiles, right? So when everybody starts doing this, then you might see after some time the same problem might pop up. If everybody shifts the load by 2 or 3 hours, it just means that the peak is just delayed, right? So this is where there has to be some coordination between the utility and so some real-time pricing has to influence the shifting of the load, right? So it has to be a two-way thing. So the smart meter comes into play as the communication agent.
Thank you. The thing, the utility agent has control of managing the power supply. The other side, by use of this smart grid, can we get ownership of controlling the demand as well? The demand response is obsession. Understood.
Yes.
Because end users are in smart grids and smart connected, smart grid and smart metering, can the utility get a power capability to control the demand other than changing supply? Okay, maybe. As you said,
so yes, yeah. So again, I don't think the utility can get the control of every customer's load. Whenever they want to control it, they have that authority to do so. It's going to be, some customers will opt not to allow utility to do that. They want their own, they want to have the control. And certain customers will say, well, you can control certain loads, like change the air conditioning temperature by a certain amount of degrees. Maybe you can delay my washing machine or dryer or something like that. So certain fraction. And sometimes, if you're not at home and you're on vacation, so there might be certain periods where you can give more authority to the utility. So I think demand response will have differentiated contracts with the customers. And based on the contracts, not the utility, but I would say more of an aggregator, somebody in the middle, a middle person, a service provider, a demand response service provider will come between the utility and the customers, because I think customers will be more comfortable dealing with someone a service provider rather than dealing with the utility, because the utility wants to maximize profit. They want to sell more electricity and get more revenue. So if utility were to manage the customer loads, there's a conflict of interest. So that's why a service provider will be someone in the middle who is not biased towards the utility or not biased towards the customer, a neutral person who is fair to take these transactions. So I see the future might be, for demand response, will be to have service providers who would manage customers' loads. So you will be able to provide your schedule to the service provider, and the service provider will try to be a broker between the utility and the customers. In this case, the service provider knows at what time, which days, what loads are available for demand response participation. And I think that might be a path that will grow demand response capabilities rather than utilities trying to work with customers directly. So we had a paper in one of the conferences. Again, one of my students, Pramod Herod from University of Pradenia, he worked with me on this. He's a PhD student at Clemson. So we presented that paper on this service provider model, which was just presented this month at the Computational Intelligence and Smart Grid Symposium. I'll be glad to send you that paper if you send me an email. Yes, I think there's one more question at the back there.
One more. We know how the storage mechanisms and batteries. Based on your observations, where are we now in terms of development? And compared to where we are now, in 5 years, there will be in terms of capacities as well as the lifetime of batteries.
Yeah, definitely. Just like the cost of PV systems have dropped tremendously, the cost of battery is also dropping, but it's not at the rate at which the PV systems are dropping. Today we know that the Tesla, the electric vehicle, I believe it's the Tesla S70D, or I think 85 kilowatt hour battery or 90 kilowatt hour batteries on that car. That car cost about $70,000 today. That's the basic Tesla model, the S model. But now there is I think the new model coming up, which is a Model 3, I think. It is coming down to $35,000 or $30,000 to $35,000, half the price, with almost the same range. The The S70 range is about 220 to 50 miles, depending on how much you drive, and I think the Model 3 is also around 200 miles. So, which tells us that now the battery density is going to get twice as much, and this production is in place right now, and I think it's going to be either later part of 2017 or 2018 that these models will be out. Tesla is already constructing a gigawatt factory for gigawatt hour battery manufacturing plant in Nevada. So the batteries are why I'm saying this is to tell you that the cost of battery is coming down. And I think it will come down, but still it is much slower than the PV systems. In 5 years from now, we probably have the cost of battery definitely half the price of what is today. Ultimately, for renewable energy sources, battery is the key, the energy storage. So any form of energy storage is important when we deal with variable energy sources like wind and solar. The moment energy storage drops, the cost of electricity from renewable energy sources is going to be much cheaper than generating electricity from large bulk generation. So that itself will drive microgrids to grow rapidly from renewable energy sources, and new customers are going to probably go their own rooftop PV with energy storage in 5 years rather than going with connecting to the grid. Yeah. So which tells us that as utilities, we have to think about how we get into that business of microgrids and encourage that, because it is going to take over anyway over time.
And I'd like to invite the Secretary IESL Electrical and Electronic Sectional to conclude the report.
Okay. Good evening, ladies and gentlemen. It's my duty to deliver the vote of thanks to conclude this evening event. Beforehand, I would like to invite Dr. Udayanga to give away the token of appreciation to Dr. Vinyagamurthy on behalf of the IESL.
Welcome forward.
So, okay. First and foremost, on behalf of the Institution of Engineers Sri Lanka, let me thank Dr. Kumar Vinyagamurthy for readily accepting our invitation and for being with us here today in spite of his busy schedule as our resource speaker in this event. Moreover, we are indeed thankful to you for the selection of one of the most appropriate topics and given insight in intelligent systems application in smart grids. Thank you, sir. On behalf of the Electrical and Electronics Engineering Sectional Committee, I would thank IEEE Power and Energy Society Sri Lanka Chapter for organizing this valuable public lecture jointly with us. Also to the President IESL Engineer Jawaharlal Meegoda and Executive Secretary Dr. Pieris and the Secretariat staff for making this event a success. Finally, ladies and gentlemen, let me thank the senior members and every one of you for taking your time to be with us to participate in this event. Thank you very much and good night.